Thank you for having me. So the title is a reference to a paper by Nick and Paul and Christian Schnell from a few years back. And what I'll be going over is essentially a new and simplified proof of a theorem that they proved. So we're talking today about smooth, complex vector varieties, and we're talking about holomorphic one forms on these. So given one of these one forms, we're looking at the set of zeros of one form, meaning the set of points where the one form kills off the entire tangent space of X. And the theorem, there's a technical statement first, which tells you something about spaces of one forms which don't have any zeros. There's this dimension bound. The real sort of headline result, the one that's digestible, is a statement that if X is of general type, meaning the Kodaira dimension kappa of X is equal to the dimension of X, then every holomorphic one form has to have a zero somewhere. And so in this original paper, they use a lot of statements about Hodge modules. They use generic vanishing theory for Hodge modules, the decomposition theorem, all these kind of high-tech things to eventually prove this theorem. But I'm hoping to show you today that you can prove it in a much, certainly much less technical way. And in fact, hopefully I'll be able to explain the entire proof of modulo, a couple of small results. Now, before we get there, let me try to motivate why you could write down at least the corollary, the general type statement, where that might come from. It really goes back to this sort of classical connection between tangent vector fields and characteristic numbers. So very classically, if you have a nowhere zero holomorphic vector field, a tangent vector field, you know that all of the characteristic numbers vanish, meaning all the top degree monomials in Schoen classes. At some point in a short paper in 1974, Carroll asks, well, okay, suppose you replace vector fields by one forms, the dual objects. Do you have a similar thing? It turns out that for surfaces, the answer is yes. You only have two classes to worry about. You have the square of the first Schoen class and the second Schoen class. And if you have a nowhere zero holomorphic one form, then these classes, these numbers, that is labeled. But he also constructs a counterexample in the general case. So once you go to threefolds, there is this P1 bundle over on the given surface, and it's fairly explicit construction by taking the predicted completion of a certain line bundle. And on this threefold, the cube of the first Schoen class is non-zero. But since it's a P1 bundle over a given surface, you can just pull back any non-zero one form of the surface, pull it back to X, and you get some one form that doesn't have any zero. So this kind of ideal statement relating zeros of one forms and characteristic numbers of Schoen numbers, it fails as soon as you go to threefolds. Then a little while later, 30 years later, Hagen and Kovac observed that this example, it makes sense to separate it out using the Kodaira dimension, or at least they make that ansatz. So they say, okay, let's separate varieties by Kodaira dimension. Now we're talking about Kodaira dimension, so that's a birational kind of thing. Once we're in the birational world, it makes sense to talk about minimal varieties and the minimal model program. If you then restrict to minimal varieties, then the canonical bundle is Nef if and only if this top power first Schoen class is not zero, if and only if this top self-intersection of the canonical bundle or the canonical class positive, if and only if X is of general type. So this. And the crucial thing here is X is of general type if and only if this non-vanishing of the top power of the first Schoen class happens. And that is exactly the way that Carroll's counterexample works. It's by constructing varieties for the top power of the first Schoen class. And so they make this observation and they prove that general type of minimal implies no there's no zero holomorphic one forms. Then there's a difference. Well, I'm lumping two things together here, but this point as well is in the same paper by Alvin and Kovac. You can attack this from a slightly different angle of sort of vanishing and given varieties. If X admits nowhere vanishing from one form, then there's a generic vanishing statement due to Green and Lattice that implies that the order class and the order characteristic of the canonical bundle vanishes. And if X is of maximal orbinate dimension and the orbinate variety is simple, so it just decomposes the product, then X is a general type if and only if this order characteristic is positive. So admitting a nowhere vanishing holomorphic one form and being of general type are complementary conditions, or at least they're mutually exclusive conditions. Under this assumption about orbinate dimension and the orbinate dimension. And then, as you know, that I don't want to talk too much about, Luo and Zhang also extend the conjecture from just being about type varieties to giving this statement about the any Kodaira dimension where you this theorem one on the first slide where you bound spaces of one forms without zeros by something involving that. And they do result for free forms.
Matt, can see more about the schema of the conjecture? So except for general.
Sorry, I couldn't hear that. Could you repeat that?
Yeah, you mean the conjecture for the general Kodaira dimension? That means that the same thing true, like
yeah. So the Hartman and Kovac paper specifically deals with varieties of general type, and they don't have any statement or any conjecture for varieties that are not of general type.
I see.
So Luo and Zhang, they state a conjecture that applies to any variety and which involves the Kodaira dimension in some inequality in this bound.
Is there any progress on this conjecture?
So this conjecture, just to go back a bit, the conjecture is actually this theorem. So Hartman and Kovac state the corollary as a conjecture, and they prove it in these special cases of minimal varieties or these conditions about the native variety. Luo and Zhang state this theorem as a conjecture, and they prove it for threefold. So I wanted to try to motivate where this thing comes from. It's not quite so clear to me exactly what the motivation for this statement is by Luo and Zhang, but they do predict that this holds back in 2005. So that's what I wanted to comment on. And then, yeah, so the history here goes that you're interested in churn numbers and how they relate to holomorphic one forms. At some point, various people, these four people, Hartman, Kovac, Luo, and Zhang, they observe that there's a connection to directional geometry and to Kodaira dimension. But it turns out that there's an underlying, a little more technical statement which explains both of the conjectures eventually, but which doesn't involve directional geometry. So you're working with holomorphic one forms, and so it makes sense. Holomorphic one forms are really about the Albanese map and the Albanese variety. So once you're working with one forms, it makes sense to try to generalize your statement to be about arbitrary maps to abelian varieties in some sense, instead of just being about the Albanese map, and then to try to prove that statement. And that is what Kovac are doing in their paper. So they state this theorem where you have a map from your smooth complex creative variety to just any abelian variety. And instead of having this Kodaira dimension condition, they replace it with a concrete condition about this specific map F. Namely that you take the fluid canonical bundle of X twisted by the pullback of a negative line bundle on A. So here L is an ample line bundle on A. That's supposed to have some non-zero section. So this is a positivity statement about fluid canonical bundles, the same way that statements about the Kodaira dimension are positivity statements about fluid canonical bundles. But it's a little more concrete and it's a little more specifically adapted to this one abelian variety. So given this positivity condition, any one form that you get from A by pullback has to have a zero somewhere in X. So this is a statement about maps to different biases, and it doesn't involve any bilateral geometry. So the main part of my talk will be about how to prove this statement, but let me start by explaining how you can get back to the statement from before, how it disconnects to the bilateral geometry. So the idea here is that so G on this slide is a smooth model of the vibration of the canonical model. So this means that you know, this map is birational to the map induced by the linear system of pluricanonical bundles, or n sufficiently large. So the dimension of Z is equal to the third dimension of X. F is a fiber of G, of the entire configuration. Then there's some theory by Kawamata, 1981, that I'm going to sweep under the rug a little bit, but it says that, well, okay, first of all, we know that the third dimension of X, that together with this theory by Kawamata says that F straight X onto its combination variety. And now I can also take the composition of F mapping to X, mapping to the Abelian variety of X. I can take the image of this entire composition, and this is independent the choice of fiber F of G. So I could take any fiber F of the entire vibration, and I would get the same subset, the same subvariety of the Abelian variety of X. And because of this surjectivity, that subvariety is actually going to be a subvariety. So I can take A to be, so I construct A or define A as being the Abelian variety of X modulo, the image of fiber F under the Abelian map. So basically, I'm taking sort of the co-kernel of this map. And by construction of A as this quotient by the fiber of G, you get an induced map from Z to A. And so this is the construction underlying the proof. And this positivity condition in the theorem is basically equivalent to asking that F here factors through the target vibration of G in the sense of this diagram. So the existence of this diagram is equivalent to saying that this map F satisfies the conditions of theorem 3. And so the rest of the proof of theorem 1, this statement about zeros and third dimension, it comes down to tracking down dimensions, computing the dimensions throughout. This is the proof of construction. What I really want to focus on is this thing and not the bilateral geometry. So I just want to try to show what the construction that connects to these statements is. So this was really quick, but hopefully get some idea of how to connect. Okay. Now, and please interrupt me with questions throughout, of course. But I'm going to move on to try to explain how to do this theorem for you. First of all, the case where t is equal to 1 has a relatively simple proof if you know a little bit about kinetic dimension. In the case t equals 1, remember we have a section of the canonical bundle to just the 10 to the power 1, with by this negative line bundle. And such a section is equivalent to this non-trivial morphism mechanism. And suppose for contradiction that there's a one form pulled back from A, which doesn't have any zeros. The existence of such a one form controls a generic management statement to Green Lassesfeld, which immediately implies that if I twist the canonical bundle by some general topological triple line bundle from A, then there's no section for this thing. And you can see that this implies that there's no sections of H0, X, pulled back to alpha because of the existence of this non-trivial map. Based upon the thing as this space, and the fact that this vanishes implies that the image of X under F is contained in a general translate of the hyperplane section. Of the advisory. But if you start with one hyperplane section and you take a general translate, if X is in there, then basically X is in every translate and they don't intersect. They don't all intersect into base levels. So this is a contradiction. So the D equals 1 case is not too hard to prove if you know this in an management statement. Once you know the D equals 1 case, you might be tempted to try to reduce the general case to this. So what can you do? So if D is greater than 1, well, after a base change of A by an isogeny, like we can assume that instead of having to take the Druid canonical bundle, tensor pullback, we can actually take this whole tensor product to some power D. And the reason is that by base change by a pseudo 7 a day, we can make the L in the original statement up here. We can make that sufficiently divisible so that L itself is actually a power of some other line bundle. And then we just replace L by that other line bundle. And then we can factor it the outside. So we get a non-zero. Get some non-zero section. And then you might be tempted to take cyclic carbon. Between D along with section S or along the device associated to S. And okay, this is singular, and we don't like singular things. Let me take us through some singularities. And then you end up with this map phi. And now the D equals 1 case, or the D equals 1 hypothesis of the theorem is satisfied by Y. So you can now control zeros of one forms on Y, but you can't really relate one forms on Y and one forms on X, because this resolution of singularities can introduce a whole lot of positive dimensional components when you grow up. And if you start, even if you start with a one form without any zeros on X, once you pull it back because of the singularities up here, you can introduce a whole lot of zeros on Y, and there's no good weight control. So this kind of fails, at least when written like this, but it turns out that this cyclic covering construction and the resolution of singularities is ultimately useful, but for slightly different reasons. So I'll come back to this construction a little later in the talk. Now, Let me try to outline the strategy of brief. For the sake of notation, I'll abbreviate the space of one formed on A by B. Then the question is about this incidence correspondence ZF, which measures the points on X and the one forms on A, such that when you pull back the one form, it has a 0 at the point X. If you take the projection from X cross V to V, then the conclusion of the theorem is that ZF subjects onto V under this projection. So the way we'll approach the theorem is to construct a complex of sheaves, of coherent sheaves on its product, which is supported on this instance correspondence. And then we'll not quite work with this complex directly. We'll have to twist it to apply generic vanishing type statements. So the D equals 1 case already shows that some kind of generic vanishing could play a role, an effective role. So we're going to have to twist by general alpha. Alpha will always be a topological true line bundle coming from A. Once we've done that, though, we can take direct images of this complex along the second projection, and this will be supported in the image of CF. So a key step will be to show that these hybrid images are actually locally free sheaves on V. Now, just because you have a locally free sheaf, that doesn't automatically give you anything because the sheaf could just be 0. The sheaf 0 is locally free. But if the sheaf is 0, then the support is empty. And so this doesn't actually help you at all. So the coupling construction from before will come in, it will come into play by helping us show that there is actually some kind of non-zero gadget related to these things. So as I said before, by doing some basic change of A, we'll reduce the case where this tensor power has a section. We'll take this resolution of singularities of a cyclic cover, and then there's some notion of a pullback of it. It's not quite pullback of differential forms, but it's something that's fairly close to being pullback of differential forms. I'll explain how. I'll explain what the complex is in a minute, but it's essentially a pullback. And so when you push this forward on V, once you take push forward, you get the push forward of this whole thing, which maps to the push forward of Cy alpha. This will be locally free because of point 2. And the image of the morphism not equal to 0. So at the end of the day, we're not actually using the D sheaf locally free. We're using that these other sheaves coming from some auxiliary space, Y, are locally free. And then we're actually using X to get some non-zero subsheaf. So if I have a non-zero subsheaf, well, if I have a subsheaf of a locally free sheaf, the subsheaf is always torsion-free. And a torsion-free non-zero sheaf has support. So, well, let's call the image. Let's call the image F. Not equal to 0. The support of F will be all of V, but the support will also be contained in the image of CF. That's the strategy of the proof. We want to produce this non-zero torsion-free sheaf, which is supported in the image of this with loaded CF image. So I'll explain all these steps as we go on. First of all, let me explain the complex. So it's a complex on the product X plus V. So I won't write down the formula for the differential on X plus V. I'll just explain what the differential is in complex. But the terms in the complex are basically the terms of the ground complex of X. They're the pullbacks of the sheaves of differential forms from X to X plus V. You can write down a formula for the differential sort of locally on the product. But what I really care about today is just what the complex looks on fibers of form X cross an element of V. Right? So these slices the fibers of the second projection. And the differential on such a fiber is just going to be the wedge product with this one form. So I provide the one form omega to X, and then I can just wedge with that one form to get a map from OX to omega 1X, and with heat you get a complex. And then for the same notation, since we'll need to twist by these alphas throughout, I'm just going to put the alpha as a script instead of writing this out. And so this is the propositional proof. The observation I want to make, which I'll explain in a moment, is that this is the Higgs complex of a Higgs bundle. This Higgs bundle with underlying sheaf OX, and where the Higgs field is the wedge product with this one form. I'll explain those words in a second. So we have this, we can explain the fibers of this complex as being double complex Higgs bundles, and so the idea of the proof is to use phase change or Crowd's theorem, which tells you that if you can control the hypercohomology of a complex on fibers, and you can show that those hypercohomology dimensions are constant as you move in the base, then the hydrate images will actually be locally free. So what we'll be talking about is the hypercohomologies in these double complexes and how we can control the way that those hypercohomologies vary, or the dimensions of those hypercohomologies vary, as we vary the Higgs field. So let me review.
Yeah.
Yes, sorry, go ahead.
If proposition 4 follows from the generic vanishing theory?
So it will not quite follow from generic vanishing in the sense of coherent stuff. It will follow from these statements about cohomology jump loci for Higgs bundles in local systems.
Okay.
I'll explain that a little more later. The original proof uses generic vanishing for Hodge modules. And there's a relation between those generic vanishing statements and the kind of structure theorems that I will use, I think it's simple proof. But you don't quite need generic vanishing to do this. I'll say that more. Okay, so just for a quick review, a Higgs bundle in general is a vector bundle together with a Higgs field, which is an O-linear morphism, which vectors with itself to scale, right? So it's not a connection. Connection's not linear, but it's the O-linear version of it. The double complex is what you get when you just iterate the Higgs field, and the double cohomology is the hypercohomology of the double complex. So as I said before, we're really going to be interested in double cohomologies of certain Higgs bundles and how the double cohomology changes. Yeah, so as I said, these CX alphas on fibers are going to be double complexes of certain Higgs bundles. Some concrete examples of double cohomology. At least one concrete example we should know is if we take structure sheets that are trivial Higgs field. We can say easily that the double cohomology is the direct sum of cohomologies of the sheaves omega p. And this looks like a electric composition type thing, and that's not interesting. I don't want to say that if we're in the rank 1 case, which we will be for basically all this talk, then the Higgs field can equivalent to be described just as holomorphic one form. So if you look at this kind of thing, if you use sort of tensor junction on this map, you can cancel out these, and you see that phase that's actually just a section of omega 1. So rank 1 Higgs bundles have a simple description. They are a line bundle and holomorphic one form. So that's just not a Hodge theorem due to Simpson and others, Simpson's correspondence. I'll write it down explicitly in the rank 1 case, but of course, code in higher rank as well. And there's some moduli spaces involved. So some fairly simple ones. First is the bed moduli space, which parameterizes rank 1 local systems of complex vector spaces connect. And as an algebraic variety, it says morph is a power of C star, and C star is the power of the first base number of heads. The round moduli space of line bundles with holomorphic connections. I won't talk too much about this today, but it should be mentioned in this context. It has the structure of an affine space bundle over big zero of x as an algebraic variety. And then the double moduli space parameterizes certain Higgs bundles, certain rank 1 Higgs bundles. As I said, a Higgs bundle is just a line bundle in a holomorphic 1 form. And for purposes of this non-revealing Hodge theorem, I have to impose some vanishing of the first theorem class. This is a little stronger than what I need to break the theorem, but I'm just going to restrict to this. In this setting, the theorem is that, well, first of all, these moduli spaces are all groups under tensor products. And they're all real analytic groups, and the theorem is that there are functorial group isomorphisms between these three. So this thing on the left is in general real analytic, but not complex analytic. The statement on the right is the Riemann-Hilbert correspondence, and it's complex analytic, but not algebraic. And then additionally, there's a notion of cohomology for both Higgs bundles, bundles with connection, and local systems. So for local systems, it's the usual field cohomology. For bundles with connection, it's the cohomology of the Duran complex of the bundle. And for the double cohomology, it's the, for the base bundles, it's the double cohomology. And if you start with a point in one of the spaces and look at the cohomologies of the associated points in the other spaces, all these cohomology groups are going to be isomorphic. And if you ignore the group part of this statement, then now the statement is holding higher rank. You just need to impose the right stability conditions and interventions and fast. But in rank 1, it's correct. If I take the example from before of the trivial Higgs bundle, then the double cohomology, as I said, is some of these Q groups. And the cohomology on the right is the K cohomology of X with complex coefficients. So the non-revealing Hodge theorem implies that these two things are morphic, which of course also follows from the Hodge theorem. So you don't get Hodge symmetry out of this type of thing, out of Simpson's theorem, because these spaces generally don't have an underlying rational structure. But you do still get some kind of direct, some kind of weak generalization of Hodge composition to rank 1, more general rank 1 local systems. One other thing I want to mention here is that if you want Simpson's theorem in the arbitrary rank case, you need all this machinery about harmonic bundles and all this analytic stuff that these people prove. For the purposes of this talk, it's enough to consider the rank 1 case. And the rank 1 case can be proven without using this theory of harmonic bundles, because the underlying line bundles in the double and round moduli spaces are topologically trivial. So if you ignore the complex structure, that is the trivial C-infinity complex line bundle. And that gives you access to the Kähler metric on the underlying space X. And you can use that to sort of replace the harmonic metrics in the case. And then proving this theorem becomes an exercise in representing objects on X with harmonic forms, just using standard Hodge theory, and then just sort of decomposing them and moving things around the object. So in a certain sense, the rank 1 version of this theorem is a very weak, the proof is not very much more complicated than the usual proof of the Hodge decomposition of the cohomology effects. And of course, you're going to want the higher rank version in any case, but if you just care about this theorem and you want an easy proof of this theorem about the one forms, you can get away with fairly simple proof of this theorem. Now, what do we care about this thing? We need one more definition. First of all, another way of explaining the theorem is that the Baudelaire and Baudelaire spaces are all just different algebraic structures on the same underlying hyperkähler manifold. So for the sake of notation, I'm going to pretend that they all have the same underlying synchronous manifold. And once you fix these identifications in the theorem, that is true. And I'll let M of X denote this hyperkähler manifold, which could have one of many different complex algebraic structures. And then a subset S of this hyperkähler manifold is, we call this a linear subvariety if it's algebraic and irreducible in these three structures. And really, we could as well call this a hyperkähler subvariety because the condition is just saying that S is compatible with the hyperkähler structure. The reason I care about this definition is it's not really the definition, it's the theorem that tells you what these look like. And the theorem is that these things are linear if and only if they are linear in the sense that they're pullbacks from some complex torus. So it's really better to say that S is hyperkähler if and only if it's linear, but that's not the standard terminology. But S is linear in the sense of this definition if and only if it's the pullback of the modular space M of T along some map to a complex torus. So in the double modular space, S, as I say, it's this pullback of the translation. So in the double modular space, S looks like the pullback of x0 of T cross the pullback of the one forms on T of the translation. I want to emphasize here that the two factors, the pullback of x0 and the pullback of space one forms, have the same dimension. So the dimension of this thing is equal to the dimension. So it's kind of a square in the modular space. So S is equal to the entire double moduli space if and only if the image S is a map from the double moduli space to x0, which just forgets the Higgs field. Takes effect of x0. This is the critical fact that so S, this linear subvariety S is the entire double moduli space if and only if S dominates x0 on the reflection map. And now we get back to what we said about genetic vanishing real estate. The reason we care about these linear subvarieties from the Higgs bundle stuff is that we can define these cohomology jump loci, which, because of the previous theorem, are going to be linear subvarieties. So the cohomology jump loci are just the loci in, I'm going to care about them in the double moduli space. So in the double moduli space, they're the loci of Higgs bundles where the case cohomology is bounded below by some integer. And you can do this for every pair of integers scanner. And these loci in the double moduli space control the double cohomology of all the Higgs bundles kind of by the moduli space. So if you understand these loci, you understand the hyper cohomology, or you understand the double cohomology of all the Higgs bundles. And that's exactly what we need to understand in this theorem. Because of the non-Euclidean Hodge theorem, you could also define these cohomology jump loci in any other structure. So you could define them in the Beck moduli, in the Beck structure, or you could define them in the Durand structure, which I didn't bother to find out if you don't need it. These are usually defined in the Beck moduli space and not the double moduli space, but they are preferred in the moduli space. And because you can define these loci in any of these three structures in the same way by bounding some cohomology groups below, these commodity jump loci will be algebraic in all three of these structures, the double best and branch structures. So they will be linear subclasses. And the way I've set this up is follows almost from definitions. I can say that they're going to be units of finitely linear subclasses just because I require linear subclasses to be reduced. So this is what we need to know about exponents now. So I'll move on to the proof of this proposition. Actually, I should let me go back to your question, please. So the original proof using Hodge modules relies on generic venture statements for Hodge modules. It turns out that the generic vanishing statements that Toban Snell used originally, they are in some sense a little stronger than this theorem, in that if you put all the generic vanishing statements they have together, they're going to imply something like this theorem. So this is really a coarser version of the results that they use. The way they go about proving things is that they use the decomposition theorem for Hodge modules at some point, decompose some direct image in a certain way. And because of the decomposition theorem, you can then work with individual Hodge modules after taking this direct image. Each individual Hodge module on a satisfies some generic vanishing statement. And the total of all the generic vanishing statements for all the Hodge modules appearing in the decomposition theorem kind of implies this structure theorem. But we don't need the fine structure that they get from the decomposition theorem. That's a bit on the side. Now remember, we have this complex Cx alpha on x plus v. We have the second projection, x plus v to v. And my goal is to show that for general alpha at least, these hybrid images will be locally free on V. Now, the way to do that, like I said, we're going to use phase change. So we'll look at a function on V that sends a point in V, meaning one form, to the ith hypercohomology, the dimension of the ith hypercohomology of Cx alpha on the phi pillars of this point. And you can control how the dimensions of these hypercohomology groups vary over the base. Then some version of Krauss theorem will tell you that these hybrid images are locally free. Right, so you want to show that the dimensions of these spaces are constant as you vary omega, as you vary the one. If you rephrase that in terms of the cohomology jump loci, the statement you get is that you're fixing one alpha. We'll choose which alpha later. It will be a general alpha, but you are fixing one alpha, and then you're allowing your one form omega to vary over V. So if you look at this, this is really a space of Higgs bundles. So this lives in the double modular space of X, and this the subset, this slice, should be for all of the cohomology jump loci sigma km. This slice should be either completely contained in that locus, or it should be completely destroyed from that locus. What you don't want to happen is to have one point of this slice that's in the jump locus and one that's outside, because that means that when you move from this one point to the other point, one of these cohomology groups will jump. One of them will jump. That's what we want to do. But now the structure of these linear subbiases covers out, and this is the key step in these techniques. So for the sake of notation, I'll let phi be the pullback map from the double modular space of A to the double modular space of X. And these sigma km's are unions of linear subbiases. There's only finitely many sigma km's I need to consider before they all become empty. And each one is a union of finitely many linear subbiases. So in fact, it's enough to show that if I have an arbitrary linear subvariety S, then this slice is either, for general alpha, this slice is either completely contained in S or it's completely disjunct from S. Equivalently, I can formulate, I can tell you what that means on the double modular space of A after I pull things back. And it just means that either the preimage of S has to be the entire double modular space, or if that's not the case, which is what I'll assume from now on, then the corresponding slice on A will be disjunct from this preimage. So this is just a separate reduction. There's nothing fancy going on. Okay. And the lemma that makes this easy is that this preimage of a linear subvariety is either empty or it's a finite union of linear subvarieties itself. And the proof is very simple because phi is pullback along an algebraic map, which means that phi is itself algebraic with respect to either the double modular space structure, the Duran structure, or the Bethe structure. And one thing I forgot to explain about the Monaghan-Huck theorem is that the isomorphisms between these structures are functorial, which exactly means that they are compatible with the natural pullback maps in each structure. The pullbacks of local systems, pullbacks of bundles with connection, and pullbacks of fixed bundles are all naturally defined, and the correspondence is compatible with these pullbacks. So this phi is itself algebraic. A linear subvariety of M of x is exactly one which is algebraic in all these structures. So the pullback is algebraic in all these structures, so it's itself a linear subvariety. And then finally, if we're assuming that this preimage is not the entire double modular space, well, it's a union of linear subvarieties, and we said earlier that linear subvarieties are proper subsets if and only if they don't dominate peak zero. So they're equal to the double space if and only if they dominate peak zero. So, if we recall a linear subvariety from pullback peak zero T plus pullback of the one form from C plus some translation for some G now it's going to be from A to P. Right? And this is going to be the entire double modular space if and only if the first factor is the entire. So that's the proof of the proposition of this local freedom statement. Now all we need to do is put together the last bits. So I'll remind you of the statement. We have a section of this line bundle, coding bundle, and this pullback from X bundle. And we want to show that every one form pullback from A has a zero sum. So I'll recall a little bit of what we've already done. After taking a suitable Italian change of A, we can assume that instead of having a broken angle bundle twisted by a negative bundle, we just have a power of a single bundle P. I'll just use P to abbreviate this thing. And we can take this cyclic cover along the section. So this is default cyclic cover. We take a resolution, singularities, and then, of course, there's going to be a map called H from Y to A just by composition. And using H in place of F, we can construct a similar complex CY alpha for Y, which by the exact same formula as for X earlier. By the construction of XD as the cyclic cover related to Reliant bundle B, there's a notion of the pullback map like this. So then the CX have its terms, choose pullback of OX, pullback of omega 1x, and so on. So I can certainly pull back you need to check that filter for differential, but you can certainly pull back from here to something that involves OY and omega 1y, and so you just pull back form from X to Y. And because the construction of XT has a secret cover related to the defined number B, you can still make sense of pulling back forms after you twist by the inverse. Like it is right now. Let's check here. Once you then push forward to B, and the image is what I called F earlier. I'm putting our theory. I didn't exactly explain what the grading is. So in fact, the grading puts the preimage of x in degree negative n, where n is the dimension of x, and it puts the canonical bundle of x in degree 0. So when you take the 0th drive direct image, you're actually doing something that's related to the canonical bundle. Now, finally, F, by definition, is a subsheet of this guy. By the conversation we proved, this is locally free on D, at least for general alpha. And so the sheaf F is going to be torsion free. And by construction, it's also clear that the support of F supported on this locus that we care about of one form plus 0 for x. Simply because there's this surjective map from this complex, which is rectified as dx, which is supported on ZF. One thing I swept under the rug until now is that Cx and Cy are graded over the coordinate ring of the that's just this mesh diagram on the star, and that's it by construction. There's no magic going on here. But there's a grading floating around, and when you track down how the grading works out, in degree given by the codimension or the difference in dimensions, what you end up with on the left-hand side is inverse tensor, canonical bundle, tensor, well, twisted by this trivial line bundle. On the right-hand side, you get the canonical bundle of Y, twist, and you can, once you write out the definition of F, you can also write the sheaf on the left-hand side as is A. And this matters in injective because it's essentially just a pullback of differential form from X to Y. And Y dominates X, and so the pullback of differentials is going to be an injective map. Push forward preserves injective maps. So at A will just be the space of sections of the sheaf on the left. Or by the prediction formula, we get something familiar. So I briefly mentioned this when I discussed the was one case at the beginning. But by the same argument as I mentioned then, this space is non-zero because, well, if it was 0, it would mean that f of x is contained in the general translate of hyperplane section. And that's just not the case. That would be a contradiction. So this is non-zero. So in conclusion, f is not 0. It's torsion free. So the support is all free, but also the support of f is the same in a set of one forms that have a 0 somewhere. And so we conclude it's focused, it's all free, the so that completes the So to recap, we basically what I've done is replaced this Hodge module argument in the original paper and using Bennington theorem and composition theorem for Hodge modules, and it's been replaced by this argument about cohomology jump loci of Higgs bundles, which can be proved just by very classical Hodge theory and a little bit of linear algebra. And we can use that. So I think I'll stop there. Thank you.